Hi, my name is Emily Belovich. My senior design project was developed in coordination with Matt Granger at NASA and Dr. Fuchs at UC and involved analyzing and optimizing the behavior of an electric aircraft motor control system. NASA's X-57 Maxwell will be the first all-electric X-plane and will be flown to demonstrate technology to reduce fuel use, emissions, and noise. The final configuration of X-57 will include 12 high-lift motors located along the leading edge of the wings. NASA Glenn is responsible for providing these high-lift motors. The goal of this project is to investigate the steady-state behavior of the high-lift motors and how they will respond to disturbances experienced during flight. Then, we would like to optimize the behavior of the high-lift motor control system. This is a software-focused project and requires the use of MATLAB, Simulink, and some specialty toolboxes, all of which are provided by NASA. In addition, Dr. Fuchs is allowing me to use his 36-core computer to run simulations. Therefore, there is no cost associated with this project. This slide shows my Gantt chart. It is divided into sections based on the milestones necessary to accomplish the goals of this project. These milestones include developing a model for steady-state simulation, developing a motor model, developing a disturbance model, linearizing the model, and developing a genetic algorithm to optimize the behavior. This slide shows the Simulink model I used for the project. This model was created by John Maroli to simulate the transient behavior of the high-lift motor control system. I modified the model so it could be used to simulate the steady-state behavior of the system. Then I developed a new motor model, the block in the middle, and disturbance model, the block at the top right. The next few slides summarize my accomplishments. First, I developed a steady-state model by altering John Maroli's transient model. This involved calculating steady-state voltages and currents, and then updating various blocks and initial conditions in the Simulink model. Next, I developed a new motor model. The old motor model used a generic motor block, but we wanted to create a custom block that more accurately represents the behavior of the NASA motor. I read a journal article, and based on the article, developed an equivalent electrical model and mechanical model. Then I created a disturbance model. I read journal articles on how to model air gusts and how torque can be calculated from airspeed. I took this research and created a Simulink block that will model disturbances. Finally, I attempted to linearize the model using Simulink's linear analysis tool. Ultimately, it was unsuccessful because our model is too complicated to be analyzed using the tool. The final goal of my project was to optimize the behavior of the system. I wrote a genetic algorithm to optimize the controller gains. First, I defined an individual of the population. Each chromosome contains 6 genes, one for each of the controller gains we want to optimize. The population consists of 100 individuals. Next, I developed a cost function. The cost function is based on the difference between the desired RPM and actual RPM, and we want to minimize this number. Then I wrote the code for the genetic algorithm. First, I assign a value to each gene of each individual in the population. Then I simulate each individual and evaluate its performance by calculating the cost function. Next, I select the top performers and use the top performers to create the individuals of the next generation through crossover and mutation. This process continues in a loop for 100 generations. I am currently running and evaluating simulations using the genetic algorithm. Even with the use of Dr. Fuchs' 36-core computer, it still takes a couple weeks to simulate a population of 100 individuals for 100 generations. I will continue to work on the genetic algorithm when I return to NASA in May. We want to modify the current cost function to incorporate motor efficiency. We also want to optimize the observer gains in addition to the controller gains. Finally, I'd like to thank Dr. Fuchs and Pavlos at UC, and Matt, John Maroli, Mike, and John Thomas at NASA. This project would not have been possible without their support.